If you have a set of vectors, how can you combine them? Today, we are diving into two fundamental ideas, linear combinations and linear independence. We answer the following questions. Why do linear combinations matter? Why is linear independence important? And joining me, as always, is our curious student Hassan.
Thank you, Dr. Akira. I'm really looking forward to this. I've been looking over the lecture notes, and these concepts seem to be at the heart of everything.
Absolutely, Hassan. Let's start with linear combinations. In simple terms, what did you gather from the notes about what a linear combination is?
Well, the notes define it as taking a set of vectors, say v1, v2, and so on, vn, from a vector space V over a field F. Then you multiply each vector by a scalar from F. Let's call them a1, a2, and so on, an, and add them all up. So it's a1 v1 plus a2 v2 plus and so on plus an vn.
Excellent. You've got the definition down. Think of it like mixing ingredients. Each vector is an ingredient, and the scalar is how much of that ingredient you are adding. The result is a new vector, which is a combination of the original ones. The notes also mention some basic properties. Can you recall any?
Yes. Theorem 1 states that the zero vector is always a linear combination of any set of vectors. And also, if you have two linear combinations, their sum is also a linear combination. The same goes for scalar multiples of a linear combination. They remain linear combinations.
Precisely. Let's go through the proofs for these properties, as they are quite foundational.
Sounds good. I'm ready.
First, the zero vector. The notes state that the zero vector is always a linear combination. This is straightforward. The zero vector is equal to 0 times v1 plus 0 times v2 plus and so on plus 0 times vn. You just take all the scalars to be 0. Simple, right?
That makes perfect sense. Any vector multiplied by 0 is the zero vector, and their sum is still 0.
Next, the sum of linear combinations. If you have two linear combinations, say x is equal to x1 v1 plus x2 v2 and so on plus xn vn, and another vector, y, which is equal to y1 v1 plus y2 v2 plus and so on plus yn vn. How would their sum x plus y look?
Based on the notes, x plus y is x1 plus y1 times v1 plus x2 plus y2 times v2 plus and so on plus xn plus yn times vn. This is still a linear combination because xi plus yi are just new scalars from the field F.
Exactly. And what about the scalar multiple of a linear combination? If you have a scalar c from F, a linear combination x equals to x1 v1 plus x2 v2 plus and so on plus vxn vn.
Then c times x is cx1 times v1 plus c times x2 times v2 and so on, and cxn times vn. Again, cxi's are new scalars, so it's still a linear combination.
Excellent, Hassan. These properties look similar to the definition of vector subspaces, don't they?
Indeed. In fact, we have the next corollary. Corollary 2 states that given v1, v2, and so on, vn, from the vector space V, the set W, which is the linear combination of these vectors, is a subspace of V.
Precisely. And the proof for this is quite elegant, relying directly on the properties we have just discussed. First, W is clearly a subset of V. Then to prove it's a subspace, we need to show three things. 1. It contains the zero vector. 2. It's closed under vector addition. And 3. It's closed under scalar multiplication. We just proved that zero vector is always a linear combination, so the zero vector belongs to W. We also showed that the sum of two linear combinations is a linear combination. So if x and y belong to W, then x plus y belong to W. And finally, the scalar multiple of a linear combination is a linear combination. So if C is a scalar from F and x is a vector from W, then C times x belongs to W. These three conditions confirm that W is indeed a vector subspace of V.
That's really neat how it all connects. So the set of all possible ways to combine a given set of vectors naturally forms its own vector space.
Absolutely. These properties are crucial because they lead us to a very important concept: the subspace generated or spanned by a set of vectors. This is where why linear combinations matter question really comes into play. Hassan, what is a generated subspace?
According to definition 1, it's the set of all possible linear combinations of a given set of vectors. So if we have vectors v1, v2 and so on up to vn, the subspace they generate, written as v1, v2 and so on vn, enclosed by angular brackets, includes every vector you can create by mixing those original vectors with different scalar amounts.
That's right. It's essentially the reach of those vectors. For instance, if you have a non-zero vector in R2, the two-dimensional space, it will span a line. Any point on that line can be reached by a linear combination of that vector. The notes give an example with elementary vectors e1, e2, and so on, en in Fn, so it's an n-dimensional vector space. What do they span?
They span the entire Fn space, because any vector in Fn can be written as a linear combination of those elementary vectors.
Exactly. Now let's transition to the why linear independence is important part. This is where things get really interesting. What's the definition of linear independence?
Definition 2 says that vectors v1, v2, vn are linearly independent if the only way their linear combination a1v1 plus a2v2 and so on plus anvn can equal the zero vector is if all the scalars a1, a2, an are 0. If there's any other way to get 0, meaning if at least one of the scalars isn't 0, then they are linearly dependent.
Perfect. We call that trivial versus non-trivial solutions. If the only solution is all zeros, it's trivial. If there's non-zero scalar involved, it's non-trivial. And the vectors are dependent. Why is this distinction so important, Hassan? What does linear independence imply about the vectors?
If they are linearly dependent, it means at least one of the vectors can be expressed as a linear combination of the others. The notes give an example. Two non-zero vectors, v and w, are linearly dependent if and only if they are parallel, meaning one is a scalar multiple of the other. So in a way, one vector is redundant.
Precisely. Can you explain the proof?
Sure. The proof for two non-zero vectors, v and w, being linearly dependent if and only if they are parallel has two parts. Let's assume v and w are linearly dependent. This means, by definition, that there exist scalars a and b from the field F, not both 0, such that a v plus dw equals the zero vector. The notes then go through a process of elimination. If a is equal to 0 and b is not equal to 0, then bw is equal to 0 would imply w is equal to the 0 vector, which contradicts our initial assumption that w is a non-zero vector. Similarly, if a is non-zero and b is 0, then a v is 0 would imply v is 0 vector, which also contradicts our assumption that v is a non-zero vector. Therefore, both a and b must be non-zero. Since b is non-zero, we can divide by b and rearrange the equation av plus bw equals to 0 to get bw is equal to negative aw, which means w is equal to negative b inverse times a times v. Let c equals to negative b inverse a, so we have w equals cv, which means w is a scalar multiple of v and thus they are parallel.
Excellent explanation for the first part. Now, what about the converse? How do we prove that if w equals to cv for some scalar c, then v and w are linearly dependent?
For the converse, we assume that w is equal to cv for some c from the field f. Since v and w are non-zero vectors, c cannot be 0. We can rearrange this equation to get cv minus w equals the 0 vector. This can be written as cv plus negative 1 times w equals the 0 vector. Here we have a linear combination of v and w that equals the 0 vector, and the coefficients are c and negative 1. Since c is non-zero and negative 1 is of course non-zero, not all coefficients are 0. Therefore, by the definition of linear dependence, v and w are linearly dependent.
Fantastic, Hassan. You've clearly articulated both directions of the proof. This example beautifully illustrates the concepts of redundancy. If a set of vectors is linearly dependent, it means you don't need all of them to span the same space. One or more of them can be built from the others. Think of it like having two identical measuring tapes. You only need one to measure length.
So linear independence means each vector brings something new and unique to the table?
You've hit the nail on the head. Each linearly dependent vector adds a new dimension or direction to the space they span. This is fundamental to understanding the basis of a vector space, which we'll touch in a future video. A basis is a set of linearly independent vectors that also span the entire space. The number of vectors in a basis then defines the dimension of the vector space.
So, if vectors are linearly independent, they are essential for defining the true size or dimensionality of the space?
Exactly, and this concept extends directly to solving systems of linear equations. Theorem 3 in your notes is crucial here. It states that a set of vectors v1, v2, and so on up to vr are linearly independent if and only if the homogeneous linear equation ax equals to 0, where A is a matrix formed by these vectors as columns, has only the trivial solution. Let's quickly go through the proof. It's quite simple actually. The proof for Theorem 3 hinges on the definition of matrix vector multiplication. When you multiply a matrix A, whose columns are v1, v2, and so on, by a vector x, which consists of x1, x2, up to xr transpose, the result ax is actually a linear combination of the columns of A, with the entries of x as the scalars. So ax is equal to x1 v1 plus x2 v2 plus and so on plus xr vr.
Oh, I see. So the equation ax equals the 0 vector is equivalent to saying x1 v1 plus x2 v2 plus and so on plus xr vr is equal to the 0 vector.
Precisely. And now, If you connect this back to our definition of linear independence, vectors v1, v2 up to vr are linearly independent if and only if the only way to make their linear combination equal to the zero vector is for all the scalars x1, x2, and so on to be 0. This means the equation x1 v1 plus and so on plus xr vr being equal to the zero vector has only the trivial solution, which is exactly what ax equals to 0 having only the trivial solution means. It's a direct consequence of the definitions.
That's really clear now. So, solving ax equals to 0 is essentially testing for linear independence. And Corollary 4, which says they are linearly dependent if they are non-trivial solutions, is just the contrapositive of this theorem.
Exactly. It's a powerful connection that simplifies many problems in linear algebra. And Corollary 5 takes it a step further, connecting linear independence to the rank of a matrix and even its invertibility. If the vectors forming the columns of a matrix A are linearly independent, then the rank of A equals the number of vectors. And if it's a square matrix and the number of the vectors equals the dimension, then the matrix is invertible and its determinant is non-zero.
Wow, so all these concepts are really interconnected. Linear independence isn't just about vectors, it tells us a lot about matrices and solving systems of equations.
Precisely. In practical terms, linear independence is vital in fields like computer graphics for transformations, data analysis for feature selection to avoid redundant information, and even in engineering for analyzing systems. It's all about efficiency, uniqueness, and understanding the true underlying structure.
This has really clarified things, Dr. Akira. Thank you.
My pleasure, Hassan. And thank you for watching this video. If you have any questions or comments, please write your comments below in the comment section. And if you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.